In the last lesson, we checked whether a stack contains some value, but often we also want to know where the value is. For example, consider the following stack. Where is 17? To find 17's position, we inspect the elements one by one until we find 17. As we move down the stack, we also count the number of elements we have inspected so far. When we find 17, we stop. As before, rather than actually moving down the stack, we will pop the stack, which changes the top element. Let's illustrate this process in a table. In each step, we pop from the stack and also increase the count by 1. When 17 is at the top of the stack, the count is 3. Thus, index of 17 in stack 11, 29, 5, 17 is 3. As before, we would like to write the current find operation in terms of the next find operation. But since we need to keep the count of the inspected elements, we first convert the find operation to the index compute function as follows. Index of val in stack S is equal to the output of the index compute function, where the input stack is S, value is val, and index is 0. The expression is much longer now, but all we really have done is added one new input called index. Then we write the index compute function in terms of the next index compute function with updated inputs. When the top element of S is val, then the output of the function is the index. Here are two properties that more precisely describe index compute. If L is not equal to val, then output of the index compute function, where the input stack is L, remainder, value is val, and index is IDX, is equal to the output of the index compute function, where the input stack is remainder, value is val, and index is IDX plus 1. If L is equal to val, then the output of the index compute function, where the input stack is L remainder, value is val, and index is IDX, is equal to IDX. For example, consider the following stack, 5, 7, 8, 9. Suppose we want to find the index of 8. First, let's use the conversion property. Let val be 8 and S be the stack 5, 7, 8, 9. Then the property is index of 8 in stack 5, 7, 8, 9 is equal to the output of the index compute function, where the input stack is 5, 7, 8, 9, value is 8, and index is 0. Next, we evaluate the index compute function. Let L be 5, remainder be the stack 7, 8, 9, val be 8, and IDX be 0. 5 is not equal to 8, so the condition is met. Thus, we can conclude that the output of the index compute function, where the input stack is 5, 7, 8, 9, value is 8, and index is 0, is equal to the output where the input stack is 7, 8, 9, value is 8, and index is 0 plus 1. 0 plus 1 equals 1. So the output, where the input stack is 5, 7, 8, 9, value is 8, and index is 0, is equal to the output, where the input stack is 7, 8, 9, value is 8, and index is 1. Notice how 5 was popped from the stack, and the index went from 0 to 1. Next, let L be 7, remainder be the stack 8, 9, val be 8, and IDX be 1. Since 7 is not equal to 8, we can conclude that the output of the function, where the input stack is 7, 8, 9, value is 8, and index is 1, is equal to the output of the function, where the input stack is 8, 9, value is 8, and index is 1 plus 1. 1 plus 1 equals 2. So we can replace 1 plus 1 with 2. Next, let L be 8, remainder be the stack 9, val be 8, and IDX be 2. Since L and val are now equal, we can conclude that the output of the index compute function, where the input stack is 8, 9, value is 8, and index is 2, is equal to 2. Now, if we apply the transitive property a few times, we can conclude that the output of the index compute function, where the input stack is 5, 7, 8, 9, value is 8, and index is 0, is equal to 2. Let's apply the transitive property one more time to conclude that the index of 8 in stack 5, 7, 8, 9 is equal to 2. In the example above, we found 8 in the stack at index 2. But the value we are looking for may not be in the stack. For example, the stack doesn't contain 10. In this case, we would keep looking for 10 until the stack is empty. We would not be able to use property 2.